Welcome back everyone to the Hello World Guide. This is another episode of the OpenGL 3 renderer series, and in this video we are going to get started with our camera and viewing system in our OpenGL 3 renderer. So currently we have got a scare that we have specified using normalized device coordinates, as you can see, and that is not really that exciting because we are just specifying it using some coordinates and it is looking like a 2D picture on our screen. But in order to create a 3D effect, we need to kind of set up a camera system and a viewing system, and in order to not have to specify in normalized device coordinates but in whatever coordinate system we want, we'll also need to create a projection matrix to take into account the different screen sizes that we may encounter. So for that we'll basically use two matrices. So matrix is a pretty common mathematics concept, and for basically viewing and basically transformations and every other thing in OpenGL, for many things in OpenGL we use matrices. So for actually viewing we'll use mainly two matrices. One is the projection matrix and the other is the view matrix, and then there will be a third one called the model matrix, which we'll get into a bit later. First, for now, let's just focus on the projection and the view matrix. So in order to get started with that, let's go ahead and try to create the projection and view matrix, but we are going to encapsulate the details of that in a class called camera. So I'm going to right click here and add a class here, and the class I'm going to just call it camera, for example. Camera actually, and you can of course call the class anything you want. We are going to call it camera because that's the most sensible name, I guess, and we are going to create that class, and this class is basically going to be the one that is going to handle all of the things that we need to. And let me zoom in a bit so that you can see a bit better. And yeah, let's now start filling up this class. So to get started, we are going to have a few public variables, few public methods and some private variables as well in our camera class. So in the public one, what I'm going to do is create a well, first of all, let us also create the labels. And one thing we want to make sure is that we include GLM, the GL math library, because we are going to be using that. And we are going to create two functions here. One is going to be a GLM : matrix 4 called get projection matrix, and it is going to require to us that we give it the width and the height of the screen in order to get the projection matrix correctly. So we'll have to pass it the width and the height of the screen. We'll just say float width and float height. And the second function that we want to create is also going to return a matrix 4, so GLM : mat 4, and the function itself is going to be get view matrix, not get projection matrix. So we'll do that, and yeah, that is pretty much it. That is pretty much all we need to do for the function. Now I do not really think we need any private variables for now, so we are just going to create a few public variables. The field of view of the camera is represented by this FOV variable. Yaw and pitch represent the Euler angles, and we won't include roll because the roll is a bit harder to implement, and we don't really need to roll the camera right now. So the camera will only be allowed to rotate in two directions, and yaw and pitch are standard Euler angles, as you can see in this picture. That's basically how yaw and pitch are represented. So that's pretty much it, two variables that we'll have. And we'll have another variable which is going to be the actual position of the camera, which we'll implement as vector 3. The reason we won't use a vector 3 or something like that for the rotation is because we are not including rolls, so we are going to only have two variables here. And we are also going to create a constructor here as well for the camera, so that we can kind of initialize it in a better manner. So we are going to create a vector 3 called position, and we are going to also take the FOV, yaw and pitch as arguments. One thing that we are going to do is we are going to move the FOV to the end. By default, the yaw is going to be 90 degrees and the pitch is going to be let's just say, for example, 0 degrees. We don't really need, for the yaw we need to make it negative 90 so that it's facing in the like forward direction, and we'll need to make sure that the FOV is 60. So that's pretty much all we need to do. And of course you can set these to whatever value you like. FOV is 60. I think that's pretty awesome. So let's go ahead and now implement these functions inside the CPP file. So for this, what we'll do is just go ahead and ask Visual Studio to generate the functions for us, the actual constructor, the camera one, and we are also going to implement get view matrix and get projection matrix as well. We'll implement those functions, and now we'll open up the camera.cpp file. Now inside of here we'll first initialize all of our variables in the actual camera.cpp. We'll set position, initialize position and yaw and pitch and FOV, everything according to the things that we have got. So that is pretty easy to do. And what we'll do next is we'll need to go ahead and implement the other two functions. For now we'll start with projection matrix, since that is a bit easier. First you want to ensure that you include matrix transform, and then we are going to just return. You can use glm ortho to set a 2D orthographic matrix, but since we want 3D we'll use perspective. And we'll pass the field of view first, but we expect it to be in radians. So if I were to open up the documentation by control clicking on this, actually this is not the actual one, yeah, like here you can see that it requires it to be in radians. So what we'll do is we'll just, and by the way it requires all angles to be in radians pretty much in pretty much every mathematics, so we'll need to make sure that we specify the field of view in radians as well. And you can see that the aspect is supposed to be the ratio of width to height, so we'll just say width divided by height here for the aspect. And near and far plane represent how close or how far we can see. We need to make sure that the near is not, if you make the near 0 nothing will work, so we are going to set it to 0.1, and for the far we'll just say 100. So now it is time to implement the actual view matrix function. So in order to calculate the view matrix, what we'll do is we'll go here and we need to calculate a bunch of things in order to calculate the view matrix, which means that we need to actually calculate the directions of the camera. So for actually getting the view matrix, we use a function called glm look at, which requires us to provide an eye, which means the actual position of the camera. The center would be basically be where the camera is supposed to be looking at, and the up direction is the up direction of the camera. So we need the forward and the up direction of the camera. So we already have got the position, so we just need to calculate these two. Now how are we going to calculate these? The first thing I'm going to do is I'm going to create a static constant glm vec3 called world up, which is going to represent where our world is up. So this is going to be constant, which means it's going to basically be staying the same. We are going to initialize it to be the y up, because y is the up direction that's supposed to be, and by the way it won't allow you to initialize a static variable inside of the class, so we'll have to cut it from here and initialize it inside of the camera.cpp here. So we'll just say const glm vec3 camera world up, camera world up, and initialize it like that. And the y is going to represent the up direction in our thing that we have got here. And get view matrix, yes, we have got that. And what we are going to do is we are going to create a glm vec3 called front, and actually let's call that forward, because that makes a bit more sense, I guess. And we are going to, you might say forward, we are going to initialize each of the components separately. So let's just use a constructor here, and for the x value we'll have to actually get the cross, or sorry, not the cross, the cosine. So we'll get cos of the actual yaw value that we have got, and we need to convert everything to radians because glm expects the arguments to be in radians. So we'll get the cos of the radians of the yaw value that we have got, and since it's easier to specify it in degrees, we'll actually use degrees here. So we'll just say glm radians, and we'll convert the yaw to radians, and then we'll basically take the cosine of that, and we are going to copy this and paste this here, and we are going to have to multiply this by the cosine of actually, yeah, we'll have to multiply it by the cosine of the pitch here. For the y and z values, we just do it like this. For the y it will be sine of pitch, and for the z it will be sine of yaw multiplied by cos of pitch. And now we'll need to actually first, let's before we calculate the right vector, we need to normalize the forward vector. Normalizing means that we divide the vector by its length, so that its length is, the magnitude of the vector needs to be equal to 0, so it only represents a direction and no actual magnitude. So what we are going to do is we are going to say glm vec3 here, and we are going to create the right vector. Now you might say that we don't need right, we only need up, but in order to calculate up correctly we need to actually calculate right first. So for this we'll have to use the cross product, so we'll do glm cross, but since this vector also needs to be normalized, we'll first call normalize. Inside that we'll call cross here like that, and inside of that we'll take cross of two vectors. The two vectors are the forward vector along with the world up vector, so the up direction of the actual world. And now for calculating the actual up vector, so this is the actual up vector of the world, and now we need to calculate the up vector of the camera. For that we'll also use a cross product, so we'll normalize that of course, and we'll say glm cross, and for actual cross we'll pass in the the right and forward vectors, and that should give us our 3 vectors. Now for actually calculating the matrix, we'll just return glm colon colon look at, and for the look at we'll just pass it will generate a matrix automatically. We'll pass the position, and for the where we want to be looking at is going to position plus forward, and for the up direction we'll just pass in the up. Then that is pretty much all we need to do to generate our matrix, and our get view matrix function is now complete. So yeah guys, this is pretty much it for this video. In this video we created a camera class and basically set it up so that we can kind of use different things here. So like how we do camera and projection matrix and view matrix, we basically set all of that up, and this is pretty much it for this video. And in the next video we are going to be learning how to use this camera class to kind of make it so that we can actually view this mesh in 3D and kind of move around as well, and implementing those stuff we'll do in the future videos. So make sure to stay tuned for that and share this video with other people as well, and make sure to like and subscribe, and I'll see you in the next one, and bye.